We have one more important standard form to consider in construction of Bode plots, and that is the second order system that may contain a resonance. Here's an example of a two-pole low-pass filter that contains an inductor and capacitor. And these LC type filter circuits commonly appear in our converter models, and in fact we've seen them already in the canonical model last week. So if we solve this circuit to find the transfer function from input to output, we're going to call it G of S in this lecture. We can do the analysis and find that G of S is given by this expression, which has a quadratic form polynomial in the denominator. So this quadratic or second order polynomial we can write in general like this, where a1 and a2 are the coefficients of s to the first power and s to the second power. And by equating a1 and a2 to the coefficients L over R and LC in the original transfer function, we find that a1 is L over R and a2 is LC. So, in a case like this, how should we draw the Bode diagram? Well, one approach, I think the most straightforward way, is to factor the denominator. We already know how to draw the Bode plot of a single pole, and so if we could factor the denominator, the second order system, into two single poles, then we might perhaps apply the methods we've already talked about in the preceding lectures. So here is our polynomial in the denominator. We could factor it with two roots, and here I've denoted the roots as S1 and S2, and using the quadratic formula, here are the solutions for S1 and S2. So as usual, it contains a radical, and the quantity inside the radical is the discriminant, and so we have the case where it's possible for the discriminant to be negative and we can get complex roots. So this indeed can happen. So in the case then where the discriminant is positive and we have real roots, then we can go ahead and factor it this way and then construct the Bode plot as two real poles in the way that we've already been talking about. Although I'm going to talk a little more about that in the next lecture, and there are some perhaps even easier ways to do it than that. But in the other case, where the discriminant is negative and we have complex roots, then we really can't use what we've already talked about in the case of the single pole. It doesn't apply. Here, going back to the slide from the previous lectures for the single pole, what we did was we let S equal j omega and found what G of j omega was for the single pole case. We got this expression, and then to write the equation for the magnitude, we found the square root of the sum of the squares of the real and imaginary parts, and while I didn't point it out at the time, there was an implicit assumption there that omega naught is a real number. If omega naught is complex, which happens in the complex roots case, then we're not correctly finding the real and imaginary parts. So the single pole derivation from the earlier lecture assumes that we have real poles, and it's not valid in the case where we have complex roots. So in the complex case, what we're going to do instead is define a new standard normalized form for the second order type polynomial, and then derive the magnitude and phase asymptotes without assuming that we have real roots. There are two forms that are in common use in the control business for the second order case. The first one uses a damping factor called zeta here, this quantity, and the second uses a Q factor here. And you can use either form. In fact, just from equating the coefficient of s to the first power, apparently 2 zeta is the same as 1 over q. In the case of the Q factor, this is in fact not the most general way to define Q, and in the RF business, the Q is defined in a more general way So we can talk about the Q factor of a single component, such as an inductor. And the Q factor is a measure of how ideal the inductor is and how large the loss is. So Q actually comes from quality factor, and it's most generally defined in this way as 2 pi times the peak stored energy in the element divided by the energy dissipated per cycle. So we can talk about the Q of an inductor, whereas with a damping factor, this is really defined in the context of a second-order system. Now, this definition of Q is actually consistent with this one in the second-order system, but the second-order system definition is perhaps more restrictive. This is a nice form to use, though, with Q, because we're going to see in a minute that it has a very nice interpretation on the Bode plot. Okay, so here was our original transfer function for the two-pole case. We can equate the denominator polynomial to the denominator polynomial in our standard form and get analytical expressions then for the omega naught and the Q in terms of the original component elements. So by equating the coefficient of s squared, we have s squared, for the s squared terms, LC in this form is equal to 1 over omega naught squared in this form. So we can solve for omega naught. And what? Omega naught will be 1 over root LC. Or F naught, which is omega naught over 2 pi, then is 1 over 2 pi root LC. Knowing that, we can also solve for the Q. So in our standard form, 1 over Q omega naught is equal to this term L over R. So we can substitute in our omega naught into there and then solve for Q. And if we do that, here's what we get as the expression for the Q for this circuit. Okay, given the standard form, let's work out what the magnitude and phase asymptotes do. So we can take the same approach as in the real pole case, let S equal j omega and work out the magnitude. And if you do that, here's what we find is the magnitude. This term on the left here, it comes from the real part squared, and this term comes from the imaginary part squared. So we can find the asymptotes. What happens for omega much less than omega naught at low frequency? Well, when omega is much less than omega naught, then this term here is small compared to 1. And this term is also small compared to 1 if we let omega be low enough. And the whole thing just goes to 1. So our low frequency asymptote, as in the case of the real pole, is 0 dB or 1 for frequencies sufficiently less than the corner frequency F naught. In the high frequency case, where omega is much greater than omega naught, then which term dominates? Well, this term here goes like omega over omega naught squared and then squared again, so to the 4th power. And if omega is much greater than omega naught, then this term will be large compared to the 1, so we can throw that out. This term here goes like omega over omega naught squared. It doesn't get large as fast as the omega over omega naught to the 4th power term, though, so this one doesn't dominate. It's this one that dominates at high frequency. So the magnitude of G then will go to 1 over the square root of just this term, omega over omega naught to the 4th power, which is omega over omega naught to the minus 2 power. Or in terms of F, we can write it as F over F naught to the minus 2 power. So this is an asymptote with a slope of the minus 2 power times 20 dB per decade, or minus 40 dB per decade. It intersects the low frequency asymptote at the corner. So I think this is a nice set of asymptotes. It is in fact consistent with what you would expect from two poles if they were real and were both at F naught. What remains is to investigate what happens in the vicinity of the corner frequency and see the deviation from the curve. So as in the real pole case, what we can do is evaluate the exact transfer function or the exact formula at the corner frequency omega equals omega naught. So at omega equals omega naught, what we get, if we just put omega naughts in for the omegas, omega naught over omega naught is 1. So we'll get 1 minus 1 squared, which actually cancels out. And the real term that came from both of these adds up to 0. And we're left with the term that came from the complex part, and omega naught over omega naught quantity squared is 1. So the whole thing goes then to 1 over root 1 over q squared, which is just q. Okay, so that's an interesting answer. It says that the value of the exact function at the corner frequency is equal to q. Well, how large is q? The fact is that q can be absolutely anything. And it's interesting that the quantities that determine the asymptotes, say the low frequency asymptote is determined by this term, high frequency asymptote is determined by this term, and the exact value at the corner frequency is determined by this term. So q doesn't matter anywhere except at near the corner frequency. And q can in fact be absolutely anything. In a passive circuit it's a positive number, but that's all we can say about it. So in fact, if we go back here, q appears only in this term, and it's equal to r root c over L. And we can make r be anything we want, from 0 to infinity, which means q can be anything. So what determines the actual function at the corner frequency has nothing to do with the terms that determine the asymptotes away from the corner. If q is large, then the function, say, q is 1,000,000, the function will go up here to 1,000,000, and it'll look like this. If q is a small number, 0.01 down here, then the function will go down there. So we can get an exact function that deviates wildly from the asymptotes at the corner frequency. And this behavior is in fact characteristic of a resonant circuit, where at this resonant frequency f0 we get solutions that deviate substantially from what happens at other frequencies. Okay, how about the phase asymptotes? Well, we can find the phase of g by finding the arctangent of the imaginary over real part, as we did in the real case, real pole case. So if we do that, here is what we get. We can plot this function as usual, and with a computer drawn plot, here's what it looks like. The curves tend to a low frequency asymptote of 0 degrees and a high frequency asymptote of minus 180 degrees, as you would expect two poles to do. And then in the vicinity of the corner frequency, the change from 0 degrees to minus 180 degrees becomes more sharp as you increase the Q factor. So we can think about some mid-frequency asymptote, say that does this to change from 0 to minus 180, and how steep this asymptote is, or how steep the change is, depends on Q. All of the functions go through minus 90 degrees at the corner frequency, but then the slope here depends on the Q factor. As in the real pole case, we can try to derive an asymptote for the mid-frequency phase. We might take the same approach as in the real pole case, where we could at first try to find what is the slope of the actual phase function at the corner frequency f0. And if you do that and draw an asymptote like this that has the same slope, then what you find is that the break frequencies here and here have this e to the pi over 2 factor, like in the real pole case. Recall e to the pi over 2 is approximately 4.81. but then it's raised to the 1 over 2q power. So this break frequency right here is f naught times 4.81 to the 1 over 2q power. Likewise, this break frequency is f naught divided by that quantity. So we have the same choices as in the real pole case. We can use 4.81, or we could round it up to 5, or we could round it up to 10. And what I would say here is that to keep our asymptotes consistent in the real and complex pole case, and in fact to get the same answer at q of a half, which is the boundary between real and complex poles, we should use the same factor here. And so what we're going to do is shown here. We're not going to quite do this. We're going to use the approach shown here, where this break frequency right there is 10 to the 1 over 2q power times f naught, and this one is at f naught divided by 10 to the 1 over 2q power. Here's a sketch of what that asymptote looks like compared to the real curve, and you can see that the actual curve crosses this asymptote at 3 places. And so this approach, or this way to draw the asymptote, is not a bad approximation. Incidentally, what this choice implies then is that the slope of the asymptote turns out to be minus 180 times q degrees per decade. So if we have a q of 2, then we'll have a slope of what? Minus 360 degrees per decade. The larger q is, the more negative this slope is, and the closer we get to just a step change from 0 to minus 180 in the vicinity of f naught. To summarize, here is a plot then of what the actual curves look like. These are nice computer-generated plots of the magnitude and the phase response for different values of q, and they're drawn in the vicinity of the corner frequency. So again, as q gets larger and larger, we get a response that has more peaking in it, which is called a resonant response. The phase changes more abruptly from 0 to minus 180 degrees in the vicinity of resonance, again as q is increased.